Greetings, Martin here, founder of FutureProof. Going to go through this presentation on mechanistic interpretability, understanding the black box. So mechanistic interpretability, a bit of a mouthful, but basically understanding how AIs work on the basis that the large language models are basically things that we've grown rather than programmed. In other words, their behaviors, understanding kind of emerged just as we add in more compute without humans actually coding it all in. This means they're a bit mysterious or a black box. So we use mechanistic interpretability, hopefully to get nearer to understanding them. So as artificial intelligence systems grow increasingly complex, understanding how and why these models make decisions becomes absolutely crucial. As we said already, mechanistic interpretability, or MI, aims to reverse engineer the internal reasoning processes of trained neural networks. Rather than treating AI as a black box with only observable inputs and outputs, MI examines the computational mechanisms and learned representations within these models to provide a causal understanding of their behavior. So what is mechanistic interpretability? Mechanistic interpretability is the endeavor to precisely map out the algorithms and circuits that emerge within a neural network during training. It's akin to dissecting a complex machine with billions of interconnected parts, identifying each component's role and tracing the flow of information to understand how it collectively performs tasks. Features. We have specific properties or patterns that a neural network learns to recognize and process. These building blocks range from low-level patterns to high-level concepts, existing at various levels of abstraction within the network's layers. Circuits. These are specific subnetworks or groups of interconnected neurons that work together to implement a particular computation or behavior. For instance, a dog detector circuit in an image recognition model. If we can get anywhere with mechanistic interpretability, if we can identify the dog detector circuit, we can understand when the AI has that specific concept in mind. Linear representations. This relates to how information is encoded in activation space, where features are often represented as linear directions, allowing researchers to track how information is transformed through different layers. Why does mechanistic interpretability matter? The importance of mechanistic interpretability extends far beyond academic curiosity. It is increasingly seen as crucial for the safe, reliable, and ethical deployment of powerful AI systems, particularly large language models and other generative AI. AI safety and alignment. This helps ensure models are aligned with human values by detecting unsafe cognition, preventing jailbreaks, characterizing dangerous knowledge, and enabling targeted interventions. We've got various blog posts and videos on the issue of human values because it's not quite as straightforward to identify those in the first place, but that's a topic for another day. Trust and accountability. This provides the why behind an AI's output, offering rigorous causal explanations which are crucial for high-stakes applications like healthcare and finance. Scientific discovery. This offers a microscopic theory of deep learning leading to improved model design, prediction of emergent capabilities, and bridges to neuroscience. AI safety and alignment. One of the most pressing concerns in AI development is ensuring that models are aligned with human values and intentions, however those might be defined. Opaque black box models pose significant risks because unexpected or harmful emergent behaviors can arise that are difficult to predict, detect, or prevent. Hopefully through this process we'll be able to detect unsafe cognition, we'll be able to identify undesirable internal states before they manifest. To do that, we need to be able to prevent jailbreaks. We need to be able to block attempts to bypass safety filters. To do that, we need to characterize dangerous knowledge. We need to determine the harmful information a model possesses. We also have to control and correct behavior. We need to apply targeted interventions to problematic components. Current state of play. Mechanistic interpretability is an active and rapidly evolving field with significant research efforts from organizations like Anthropic, DeepMind, OpenAI, and Redwood Research, alongside numerous academic groups. Despite notable progress, it faces substantial challenges as models grow in scale and complexity. Feature and circuit discovery. This is the challenge to identify the specific features, for example curve detectors in vision models, and simple circuits, such as induction heads, in transformers that enable in-context learning. Activation and path patching. These techniques involve swapping activations between models or within a model to understand causal pathways and trace specific flows through the network. Neuron visualization. These are methods to visualize inputs that maximally activate specific neurons, revealing the features these neurons are detecting. Finally, we have sparse autoencoders. This is being explored as a method to decompose high-dimensional neural activations into more interpretable or sparse features, addressing polysemanticity issues. In other words, the fact that at the present time, with all the floating point numbers in there, sometimes we can't identify exactly which concept or word is being triggered within a particular neuron or neuron sets. It could have, therefore, many different meanings or polysemanticity. Challenges and limitations. Despite promising advances, mechanistic interpretability faces significant hurdles that researchers are actively working to overcome. These challenges range from technical limitations to fundamental questions about the nature of interpretability itself. First, we have scalability. Applying MI techniques to state-of-the-art large models with billions or trillions of parameters remains difficult. Manual circuit analysis is incredibly labour-intensive. Polysemanticity. As we've seen, this means situations where neurons often encode multiple seemingly unrelated concepts, making it difficult to assign a simple singular role to a particular neuron. Non-linearities. Understanding how non-linear transformations affect feature representations and circuit behaviour is complex. Defining interpretability. There's ongoing debate about what constitutes a truly interpretable explanation and how to measure the effectiveness, therefore, of MI techniques. Critiques and future directions. Some critics argue that despite significant investment over the past decade, mechanistic interpretability has yet to deliver substantial practical returns for general-purpose state-of-the-art AI systems. They cite instances where early interpretability findings were later found to be misleading or not robust. Future directions include conceptual improvements, developing better theoretical frameworks for understanding neural networks. Methodological advancements, creating new techniques for probing and understanding model internals. Increased automation, building tools to scale interpretability to larger models. Imperfect interpretability. This means understanding enough to ensure safe boundaries rather than having complete transparency and understanding of everything. The future of mechanistic interpretability. Research is expanding to new domains like vision language models and exploring how MI can predict emergent capabilities and improve training processes. The ambition remains to develop an MRI for AI, allowing a deep mechanistic understanding that could unlock unprecedented levels of control and insight into artificial intelligence. Neuroscience parallels. Here we can draw inspiration from how we study biological brains to better understand artificial ones. Emergent capability prediction. This means using MI to forecast when and how new abilities will emerge in larger models. Representation engineering. This involves controlling high-level concepts within models for safer, more reliable AI. Cross-domain applications. This involves extending techniques to multimodal models and diverse AI architectures. That's it for now. Thanks for watching and hope you found that useful. Please explore our website for more blogs and videos on this and other AI topics.